So I'm going to quickly go over assignment our third lab, which is basically a math assignment. But the nice thing about it is that it's a lot less stressful than any math assignment you've ever done. Okay, so modules. Module 3 is all about big O notation. Um, I don't know why I keep having this over here because all these things are just big O videos. Just watch the videos, do the thing. So these are basically so runtime analysis is something you should be doing in, I think, either 1166 and or 2166, right? Um, that is where a lot of the formal mathematics come in, especially if you're computer science doing 3223. So my goal of this class isn't to retread ground that you've already had, but rather just try to present it from a more, I guess, IST perspective, a more layman's perspective of just kind of getting a feel for what these runtimes feel like. Okay. Um, so at the end of the day, we've got these runtimes. Okay. And what we do with these runtimes is that we use them to kind of compare our algorithms to each other, because saying, hey, my algorithm took this amount of time to run on my computer doesn't really present us with a lot of effective information, right? Because my computer could be really powerful, and the algorithm that I'm comparing against, if you're using a dinky old laptop, that's not going to be a fair comparison. So instead, what we use is big O notation, right? So share for a second, share whiteboard. So big O notation kind of looks, basically, you'll see it in the form of here's an O, and then there's some value over here, and I'm just going to put a question mark, okay? Some value inside this O. Now, for those of you who are mathematically inclined, and more mathematically enthusiastic, a lot of times you'll see big O of like n squared, and you'll see a computer scientist write big O of n squared. And what they mean is big theta of n squared. And that will annoy you to no end, and you're just going to have to deal with that. Um, so, so for everybody else, don't worry about that, because it's your chance to annoy the mathematicians. All right. So anyway, what does this mean? Basically, the idea here is that we want a brief mathematical statement to say how effective our algorithm is going to be. For this class, you'll be learning basically 5 different big O um, kind of notations, starting with these 3. The first is constant time. This means that if an algorithm is O of 1, it means it doesn't matter what size I put in, what my input size is. Like, it's just going to take the same amount of time to do this algorithm regardless. So, for instance, to tell me how big a string is, right? If I ask for string, if I'm asking for like string dot length, that's going to be O of 1 no matter what, right? Because it doesn't matter if it's a tiny string or a big string. It just has that variable saved. It's going to give me the amount of time. So sorry, it's going to give me the size of that string no matter what. Um, O of n algorithms are probably the easiest ones for us to understand. For instance, if we wanted to count, and using our string example again, right? If we wanted to like count the number of vowels in a string, that's an example of an O of n algorithm. Now think about how you would have to do that, right? You would have to go through every single letter. If we've got some string here, right? then we have to go through every single letter one at a time and check if they are A, E, I, O, or U, right? So if so that's going to take basically one operation, let's say, per letter. I know we have basically 5 because you have to do 5 separate checks, but basically each letter gets checked atomically. If, for example, somehow we do a string of one more letter, it's just going to take one more operation. If our string is now twice as long, it's going to take twice as much time. This basically defines a relationship between the amount of n and the amount of time it takes that looks something like this. Whereas our O of n, sorry, O of 1 time looks something like this. Does that make sense so far? So no relationship between our sizes, a relationship between our input size and our time, and then we have O of n squared. All right. Now let's go back to our O of n example. Now, typically, if I am grading, right, if I'm grading exams with my TA, if I have 30 exams, let's say each exam takes me 5 minutes to grade, then it would take me 180 minutes to grade them. Sorry, 105 minutes to grade. Whew. It would take me 150 minutes to grade them all, right? So I can kind of do that math very quickly. And again, with this O of n relationship, right? If I doubled the number of exams, I have, each one still takes me 5 minutes to do. And now it takes me 300 minutes, twice as long. However, now let's suppose that I'm very paranoid about students cheating, right? Rather than grading each exam kind of as their own individual unit, I have to check every exam against every other exam. Okay? And so here are 3 exams, right? I'm checking each of them against each other. And now if I add in another exam, I have to check this one, and this one. And then if I add in another exam, I have to check this, and this. And if I add in another exam, I have to check here, here, here. Notice that basically each one I add adds more and more work I have to do. Right? So if I've got 30 exams, right, and I'm being paranoid and checking each of them against each other, right, I don't know how long that's going to take me. But what I do know is that if I have like a student who takes their exam late and I'm being paranoid, which I'm not, I don't do that, but I'm just kind of saying for the sake of this argument, if I have one extra exam that's late and I have to check, that means I have to check it against 30 other exams. Here, adding one exam meant adding one more work. But in this scenario with O of n squared, adding one more exam meant adding 30 more work. Does that make sense? Or another way to put it, here, times 10 exams meant 10 times 10 the amount of work. In this case, times 10 the exam means times 100 more work. It's this squared over there. The relationship, so this occurs in problems where we do a lot of comparing against each other, like our more basic sorting algorithms, like selection sort. So basically where we go through and everything, and basically every item has to be compared to every other item in a list. Make sense? So basically a good way to think about it is we don't bother iterating through. We iterate through a list using our algorithm, and basically we touch each item once. And here, for each item, we need to iterate through the list. And this actually kind of basically goes to, you can kind of almost eyeball it with, say, basically there's no for loop, O of n means you have one for loop, and O of n squared is often, but not always, a nested for loop. And it's basically too deep. Now there's other like I mentioned, we also have other runtimes, right? So I mentioned we have O of 1, we have O of n, O of n squared. In this class, we'll also learn later on two other runtimes, O of log n and O of log of n log n. And I know some of you are screaming right now because logarithms are terrible and they were hard and complicated and they don't make any sense. I promise you, after being with me, logarithms will make sense. You might not be able to compute them in your head, but they will make sense as a mathematical tool that you can use, which is different than the definition. We're not looking for definitions here. We're looking for tools we can use. That's the difference in this class versus, say, a more formal mathematics class. And I do more formal mathematics, but I understand where my audience is, and I understand where we are in our objectives. So, there are other now these aren't end all be all runtimes. Some algorithms we just can't do any better. So, for instance, O of say 2 to the n, where the n is in the exponent. That's a bad runtime, where basically each step doubles the amount of runtime. And then, of course, we have our good old classic n factorial, where that's basically every possible permutation needs to be checked of a problem. And those are terrible runtimes, but we don't encounter those too often. Now, this O of n tool is typically, this is the last thing I'll say on this. This O of n is typically used to measure time. Okay? We typically use it to measure time. But we can also use it to measure other things. We can use it to measure the amount of space a problem takes up. In other words, how much extra memory you need to use. We can use it to measure the amount of energy that gets consumed by a problem. We can use this to, and let's see, another one I've seen used is the amount of error. Okay. But really, the primary use for this is measuring this one. And the reason being, okay, why do we use O of n to measure time, and why don't we concern ourselves with the other one? Space, you can always buy, right? I know RAM is super expensive these days. It's not always going to be super expensive. It fluctuates and goes. Hard disks, same. You can go out and but you could ostensibly go and buy more space. With energy, you can do the same. You can go and buy more energy, right? We can, right? You can always go and get more power or build more. It just requires money. Error is rare, right? You don't really care about that unless you're doing approximation algorithms. But time, you cannot spend money, right? You can't go anywhere and say, I'd like one more day, please. I'd like 5 more seconds. Time is our most finite, most valuable resource. Okay? And it is precious. And so it is something that, and I urge you, just kind of outside this class, to kind of be aware of that. Time is precious. You don't know how much of it you have. Okay? And so it is our most important resource. We cannot buy more of it. And this is reflected in our problems as well. Now, with regards to the actual homework that you'll be doing after you watch these videos, um, our assignment is actually fairly straightforward, right? Be sure to do the quiz. And then over here, we have our big O notation. It is a, I have some kind of basic rules as a reminder, if in case you didn't watch the videos. And again, if my stuff is incomprehensible, uh, big O is kind of the area I'd say I worry most about my videos. I think they're pretty good, but if you need to, feel free to check out other people's videos, right? Simple first, take these T of M, which is the traditional way to say this algorithm's runtime is equal to this, simplify it into big O time. I will be going over problems 3 and 4 in class and giving you those answers on Thursday. Why? Because unless you know the triangular number series or have done convergence in Calculus 2, you'll most likely get these wrong. So I will do those in class, but feel free to look them up. I highly recommend just kind of plugging them into Google and looking up what they give you. Okay, what is the time complexity to get an item from array list? Just kind of asking you to analyze the array list that we've been looking at. Here is a problem from a puzzle book that I've always loved as a kid. This is a problem, and this is actually a computer science problem. The instructions for the problem are here on the side, right? And so kind of as to how to solve this. It's all part of like a big puzzle series. The Maps and Mazes is what's called. Anyway, so basically I want you to go onto Wikipedia and look up the problem and then kind of abstractify it. Finally, 2 more pages. BOGO sort is one of 2 algorithms that don't exist in real life. They exist only in your classes that teach runtime notation. BOGO sort is actually a pretty darn hilarious algorithm. Basically, it says while not sorted list. I'm typing it out here, and then it should hopefully appear on the screen. That is your algorithm. Everybody see it in blue? Did it appear on the screen? Great. While not sorted list, shuffle the list. While the list is not sorted, shuffle it. That is the entire algorithm. I want you to basically analyze how long that takes to run. Okay. And the good thing, and I would highly recommend, this is actually the Wikipedia article has a pretty darn good write-up on it. So go feel free to do Wikipedia. Finally, the last part that you cannot look up on Wikipedia, for each of the methods you wrote in lab 2, figure out the time complexity of the method you wrote. And I'll give you a hint, by the way. For the algorithms you wrote, right? As I mentioned in class, we are only considering 3 runtime algorithms right now, right? Where we are. Okay, these 3 runtimes. And I can pretty much guarantee you that none of my problems could be solved in constant time. So the algorithm you wrote is either O of n or O of n squared unless something went horribly wrong. Okay? So, and the last thing 2 last things. First, how do we turn it in? And second thing, exam. So I'll do the exam. Actually, I'll talk about exam first. For the exam, how much of big O stuff are you required to know? There will be a question about comparing and contrasting array lists and linked lists. You're going to be expected to use big O notation or terms like constant time, linear time when you're discussing the comparison. Okay, that's one thing. But a very common thing I ask is essentially what you get asked here, which is when I ask you to write a problem or write a solution to the problem, I ask you, what is the runtime of the method you just wrote? And finally, the last thing I use Big O sometimes to do is I give you a problem and I say, your problem, right? This is a whatever point problem. Like, say it's a 10-point problem. It is worth 3 points for your problem to run in O of n time. So you can write a inefficient algorithm, but it will cost you a few points, which is and honestly, when you're doing like an interview at Google, this is like the kind of thing you do where you write your inefficient solution first and then you try to refine it to a more efficient solution. So long story short, get the points get the points on the page, then go for as many more as you can score. All right, how do you turn this in? And the answer is, I don't really care how you turn it in. You can edit this PDF, like, put in text boxes on here and save it or whatnot. You can convert it to a Word document. You can open up a notepad and just kind of say, problem one, answer, problem two, answer, problem three, answer. You can print this out, write on it, take pictures of it, upload it. I do not care how you turn this in. You do what works best for you, please. Please, please do what works best for you. When you demo this, what we will do is we will go through these problems. And it's very easy for me to kind of quickly check because a lot of these are either right or wrong. And if it's wrong, I'll tell you to correct them. I'll tell you to correct them. And then uh and then I will give you your score. And then if you need to regain points on the points you missed, you just come back to me and with your fixed problems. So the goal is that you get 100 on this. It is not like a math problem where you just simply turn it in and then hope you didn't do too badly. Okay. All right. So I'm going to go ahead and stop recording because what we're going to do is we are going to split up into breakout rooms. Okay. And what I will do is I will rotate through those breakout rooms and then I will make it so let me enable screen sharing. Who can share? All participants. Who can start sharing when someone else is sharing? All participants. And what we will do is that I will create, let's say, 5 breakout rooms. Let participants choose the room. Okay. And what we'll do is that you just simply spread through however you want through the breakout rooms, and I will move through them sequentially. So I'll go to room 1, then room 2, then room 3, then room 4, then room 5, and then I will repeat until no one remains. You do not have to leave at any time, but if you would like to, you can. But I highly recommend you stay simply because this is time for you to work on these problems and get my help, right? Okay. Um, so I'm going to go ahead and open up the breakout rooms and then I'll move to room 1 and I'll help you on this problem, on array lists, on Fox and Rabbit. You want to demo something? It does not matter where you are. I will help you. Okay. You want to ask me something about a different class? Sure. Why not? Okay. So let's go ahead and create these breakout rooms and I'll head to room 1. Open all rooms and breakout room 1. And And since I'm going to room 1, this is your chance to duck out without seeming rude if you wanted to leave. Stop recording.